Hello, welcome to Freshman Orientation. My name is Dr. Edward T. Bednarz III, and I am an Associate Professor of Mechanical Engineering here at Wilkes University. So usually I hold these presentations in person, but given our circumstances this year, this one's going to be online. So I hope to convey all the information you would like to see and tell you a little about myself and uh, research work the students have opportunity to get involved in here at Wilkes, as well as primarily what is Wilkes University Engineering about. So hope you enjoy this presentation. Hope it's very informative. If you have any questions at all, please don't hesitate to reach out to me. My email address is listed here, edward.bednarz@wilkes.edu. So let's get right into it. Let's go back in time. So who am I? I thought it would be useful to kind of let you know who I am before you say, well, why should I listen to this guy? So I'm from Northeast PA. I'm from Hazleton originally, and I was a mechanical engineering student at Wilkes in kind of the transition of the new millennium. Graduated in 2001. So every year I make this, I'm like, wow, it's further and further back in time. But the good news is I've had most of the same professors that are still here. We at least have a few senior faculty that I had as when I was a student, Dr. Garishi, Dr. Razavi, Dr. Kaleem. And I can also still relate to current students since I've been in your shoes. And I'm from this program, and that's why I endorse it so highly because I think I went on and humbly say I had a successful career as an engineer before I transitioned into academia. So that's me back in the day, back in college. I had the goatee and the bowl cut look. That was kind of the fashion in the '90s, and I don't think I look that much different now. But I've aged 20 years since then. All right, so other activities at Wilkes. I played on the tennis team. It's always a common question. Can my son or daughter participate in sports while they're an engineering student? And the answer is yes. Yes, if you prioritize your time and balance um, your studies with extracurricular activities, absolutely. I was also involved in campus interfaith. I was involved in other clubs, ASME, American Society of Mechanical Engineers. So it's basically, college is an interesting period in someone's life because it's the transition into the real world. Parents are not here to tell you to do your homework, right? Professors, we do the best part we can to care. And, I do take attendance in my classes, but if you don't show up to class, I can't go knock on your dorm room and say, hey, why didn't you wake up this morning? So, it really is your transition to being an adult. And, when you're an adult, you have to show up to work on time. That's part of what's expected of you. So again, I think this is extremely relevant. What did I do with my Wilkes engineering degree? So in a nutshell, I got a full-time job working as an Army civilian, and I got to live out my dream of calling myself an inventor. So I'm going to talk a lot about what is engineering in general in this presentation. But it's a cool profession. I really do highly endorse it, and hope you get that after we're all said and done here. I went to graduate school while I was working. It's kind of another common question that I get, especially from my advisees that I meet with, every semester, and they're maybe contemplating grad school. They say, "Oh, well, should I just go right from my undergrad into grad school, or should I work first?" And it's kind of a complicated answer because it really is up to the person. But in my case, I was able to successfully start working, and then I had the Army pay for my graduate school degrees. So that's kind of one of the benefits to just to working first before you go to grad school. Of course, a drawback could be once you're out of school, you may not want to go back. So we do have opportunities here at Wilkes. Just to briefly plug what we have available here, that we have a master's degree in mechanical engineering, and if a student really does schedule their classes well, they can get both degrees in 5 years, 5.5 years, or 6 years at the very latest. So that might be something to contemplate, later on. So I did, I worked as an engineer for 12 years, but that did help me lead to my current teaching position, which is even more of a dream for me. I loved my job with the Army and I love being an engineer, but I love this 10 times more. I love working with students on a daily basis. I love teaching, conducting research, and continuing to learn myself, actually. So again, I graduated Wilkes mechanical engineering degree. Not to brag too much, but I had a pretty nice GPA. I studied hard. I worked hard. I was definitely blessed with gifts in math and such, but I did mainly work to get it. It wasn't just nothing was just handed to me. So all my students, I tell them as well. You have to work at it. I tell my children, you have to work hard in life. And nothing's just given to you. Anything worthwhile is a tremendous amount of sacrifice and work, but it's worthwhile. That's why it's worthwhile. So I graduated from UMBC, University of Maryland, Baltimore County, in 2006 with my master's degree, and then my PhD from the same school in 2012. So it took me several more years. It was kind of all but dissertation for a while. And it really took the motivation to say, hey, I really do want to finish this degree so that I could go on to teach. That was kind of, sometimes we need a little motivation. So I put up the logos for the two schools, but since this is the one that pays the bills for my family, we're going to highlight the flying W there. When I was at Aberdeen Test Center, the U.S. Army Aberdeen Test Center, ATC in Maryland, I had a lot of cool jobs I worked on. I don't want to list them all, but I just briefly show my primary mission was to design outriggers for vehicles in order to perform a lane change maneuver. So us as a testing organization, we were responsible for testing the performance of all types of Army vehicles. So smaller vehicles like Humvees, or the big, large vehicles that are the mine-resistant, ambush protective MRAP vehicles, and even higher than that, tractor trailers, whatnot. So they wanted to see how quick could it go through a lane change maneuver without rolling over. So you can tell that that's a pretty dangerous endeavor. That you don't want it to flip over. You don't want to ruin $1 million piece of equipment, and more importantly, you want to protect the driver. So I designed these outriggers, and if you can see my cursor, there's a foot pad that would skid off the ground, and this A-arm that would hold everything in place, and then there's a shock absorber that would dissipate the kinetic energy into the system. So, definitely you can see the engineering that would have to be involved in that to resist a vehicle traveling at a fairly high speed and making a quick turn from flipping over. This is another cool job I worked on. I designed modular platforms for ballistic testing. So basically, this was a big frame that we could put body armor in, and they could shoot at it and see how good the body armor is. So I got to witness some of the tests. I didn't actually get to fire the gun, but I was the design engineer. But the cool part of this job was I got to draw all this in SolidWorks. So this is all my drawings in SolidWorks, and then I got to physically build this. Sometimes as engineers, depending on where you work, you could be more hands-on than other places. Some places you're going to be literally in khakis and polo all day and just do your drawings and maybe check on the progress in the shop floor. Other places you may be expected to turn some wrenches and get hands-on. I'm going to talk a little bit more to that later on in my talk, but Aberdeen was cool that I got to do both. I got to do the design analysis, and I got to do some physical building and testing myself. And what you're seeing on the right is basically, it's called 80-20, and it's an adult erector set. That's the best way I like to describe it. It has all these different bolts and nut plates that you could slide in the slots from the extrusions, the aluminum extrusions, and you can basically configure something however you want. So, all I could do is just reach into my bin of piles of brackets and pull out the bolts, and it was kind of fun. You would have to know how to build it in the right order, because once you slid in a nut plate, you would have to slide in the proper one from the inside out. But yeah, it was pretty fun job to be working on. Then I worked for Aberdeen for 8.5 years, and then I moved back to the Poconos, and I worked for Toby Hanna for 3.5 years, also as a senior mechanical engineer. So I got 12 years total Army experience before I quit my government job and moved into academia. So while I was at Toby, I was a lead test engineer in the Environmental Stress and Screening Lab, which performed temperature and vibration testing. So we could have a shaker table to see how different piece of equipment, react it. It was mainly electronics equipment I worked on at Toby, and there was a temperature chamber that we could go extreme temperatures, cold and hot, as well as humidity extremes. Then probably the next job I worked on, possibly the coolest job I worked on, I'll show you in the next slide why I say this. I designed a 3-spar assembly for a 28-foot dish on a radio solar telescope network and installed on site in Hawaii. So this radio telescope network, there's several sites around the world, and it's basically just to kind of monitor solar flares. And it doesn't seem like a hard job. It's okay, well, it's kind of a big dish, and I designed these posts that went up and held the focal ring in place. But here's the cool part. We got to go to Hawaii to install it. So this is Kena Point. It's on the northern edge of Oahu. And there's me back in the day, on top of a 35-foot man lift on top of a 1,500-foot cliff. And I was the one that actually had to do the installation because it was kind of my design. So that was cool to get really hands-on. And I'm like, don't drop the nut, don't drop the nut. So yes, I got paid to go to Hawaii. So that's kind of a cool thing with engineering. Sometimes you work for a company or organization and you get to do some neat travel. So that was awesome. That was a fun experience. So also while at Toby Hanna, I worked on something that led to my first patent. So I'm going to talk a little about my patents and intellectual property in general coming up. But here's my very first one. It's called the safety brace, and it was for a Q-37 firefinder, which protects soldiers from being killed when working on this pretty big antenna system, a 2,000-pound antenna. So you could picture this antenna as a dump truck bed that goes up and down, and it's driven by a lead screw here. So here's the motor, and there's the lead screw that would drive it up and down. And if someone needs to do maintenance under there, basically they're only relying on the brake of the motor to keep it from falling down. So this was a physical assembly that would go in place and lock it, and then if something catastrophic happened, it would put all the load into this safety brace and protect whoever was working on it. So there was a lot of reasons that I take pride in this assembly and this design. Again, safety seems to be a theme through my career that I really I take it seriously, that I want to make sure people are protected and they could do their jobs safely. So here's my patent number, basically 8.5 million something, and it was going too far ahead. And it was awarded in 2013. Okay, so how did we get there? How did I get to the patent side? And this is, where I could talk a little about engineering in general. So first thing before I design a safety brace is how much load does it have to take? That's kind of a very basic questions that engineers have to answer. So what you're seeing on the left here with all these pretty colors is CF Design. It's basically a computer program that would help analyze wind flow. So I modeled the safety brace at its typical angle, 77 degrees here. And I said, okay, here's the wind flowing by, and how much force from the wind is acting on the antenna. So this is kind of a common tool for engineers to use a computer to help assist our work. We need to know the math and how to do a lot of hand calculations, but it's also good to use computer to help out as well. So once I know the force from the wind and I know how much the antenna weighs, here's the force from gravity, and then here's the brace pushing back at an angle. This is all called the free body diagram. And this is actually something you learn as a sophomore. These arrows represent force vectors. And in statics, which is a class your sophomore year, how do we analyze a free body diagram to calculate unknown forces? So in this case, I had two known forces, the force from the wind and the force from gravity, and my unknown is, well, what's the force on the brace? So I was able to use, and then I was able to do this step using hand calculations, actually. So I calculated from the free body diagram, assuming that this is in static equilibrium, which basically means that some of the forces equals 0. So sum of the force in the x heft equals 0, sum of the forces in the y equals 0, and then here's the force from the brace. So then I used another computer program. It's called finite element analysis, FEA. You may have heard that term. And that's going to help show the hot spots in the design. So anything that's green and blue is good to go. You can see here right at the gusset, we got this little red hot spot. So what that's showing is that's going to be your highest state of stress. And if you keep pushing, that's probably where it's going to break. You're probably going to crack that weld right there. So I did the analysis and found out that the safety factor was greater than 10, which is good. You know, it definitely should be safe under any extreme situation. You know, the antenna's up in the air and the wind's blowing violently, we should be good to go. But you know, many times and most of the time as an engineer, you don't want to trust just computer analysis or even hand calculations. You want to do physical testing. You want to see, okay, will it work? So you know, I was up at Toby Hanna at the time when I was working on this project, and I coordinated testing back at ATC, where I spent the majority of my career, and we got to put it in a big press and just kind of crush it and see how much it would break. And sure enough, it took a lot of weight before it could break. You know, I think we verified that it was a safety factor of 10 or greater. So that was a great test to do. It was kind of fun to take it to failure and break it, and then to demonstrate, yes, this will be safe. And so these braces are currently being manufactured for deployment in the field. So, and then one more thing I just want to highlight in this project before I move on to the next project. We had to build a plastic prototype before we got into full-scale manufacturing. So this was using additive manufacturing. And this is another emerging technology in the mechanical engineering field, where you know it's 3D printing, sometimes called, or vice versa. You could call it 3D printing additive manufacturing. Why is it called additive manufacturing? Small tangent. Traditional manufacturing is subtractive manufacturing. That's what mankind has been doing for thousands of years, right? You know, we take a piece of wood, we cut it, or we drill a hole in it, or right, or you could do it with steel or aluminum or what have you. Additive manufacturing, you're building something layer by layer, and in order to assemble your prototype. So this prototype, and I usually pass this around as a demo, you know, if this was an in-person orientation, but for now, just you could look at the picture. It's made of plastic, so it's nowhere near as strong as the real item, but it's there to test the form, fit, and function of the final design. So there is a pivot built in here, so this does open and close. So I wanted to make sure, does it fit around the lead screw like it should? And there's a little notch there to clear, you know, existing protrusion. So does it fit before I go ahead and create this large-scale manufacturing line? I just want to make sure everything fits how we think it should. So the rapid prototyping machine lays down plastic in 10,000 inch intervals in an iterative process, and it's basically using the CAD model from the computer in order to build it. So it's just a couple cool views showing what it looks like as it's being built. The white part is the plastic, that's what we're keeping, and the black is the filler, which is subsequently removed in a chemical bath. So you need the filler anytime you're going to try to lay plastic over air. You can't just lay the plastic, it would just droop down. So we have to build up these supports first. And then that's either chipped off or dissolved. Okay, so then that was the first patent. My second patent is the deflection plate leading into the force transducer. So the high strength deflection plate, which mounts underneath a mobile dynamometer to prevent a load cell from being overloaded. So this patent was issued in 2016. So this was kind of a fun project. This is actually my only patent where I'm the sole inventor. All my other patents, I'm co-inventors with other engineers, and in one instance I'll get to a little bit, non-engineer. But yeah, this was the only one that was a sole inventor. So it was a pretty fun project to work on. I needed to design this special taper in order to pull a tank without overloading the load cell. So I didn't want to break the load cell. So it's kind of like protecting the test equipment in a nutshell. This is the last major thing I worked on down at ATC. It's called the Bridge Crossing Simulator. So the Army tests these portable Army bridges, the green bridge there, and we can test it for fatigue life by either driving a tank over and over, or in this case, we wanted to create a machine that would do it quicker, safer, more cost efficiently. So this huge machine, the bridge crossing simulator, it pulls down with these hydraulic cylinders on these wiffle trees. And that's what actually applies the load. And it simulates a rolling load down the bridge. So we start pulling on this side and we start applying a couple cylinders and it sort of leapfrogs its way down the end. And then the whole bridge sags and deflects, and we call that one cycle, and then we keep doing that over and over and over. All right, so that was something cool I worked on, and related to that would be my patent for force transducer relating to my BCS work. So that was, and that was actually my dissertation for my PhD too. It was just ways to identify loads on a beam or bridge using strain gauges. So that's, I don't want to get too much into that at the moment. Okay, my next two patents, I'm proud to share this one. It's my co-inventor, my partner, and my wife, Heather. So Heather is a occupational therapist, and she had an idea for these two inventions, based on her experience in her job. The first one was for an adjustable wheelchair, so that it would basically grow with the patient. Wheelchairs are in discrete sizes, but she wanted to make one that would actually, you could use a crank handle and adjust the screw, and it would get bigger or smaller. So it would adjust perfectly to the patient. So there's a lot of great applications for that. That either a facility like a nursing home, they don't have to stock as many wheelchairs, right? They could, instead of having an 18-inch, a 20-inch, a 22-inch, just for all these different patients they may get, they can just stock a couple of ours, and they'd be able to adjust it. Or if a patient got sent home with from Medicare, they got sent home with a wheelchair, and then they needed a different size one as they got older, then they could adjust it themselves. The second patent I'm equally proud of was a pressure redistribution system. So if someone is partially paralyzed and they're sitting in one spot for too long, they can develop pressure ulcers, which is a very nasty thing. So we developed a system that could actively see if they were sitting in one place too long, and then it would sense it and alert the caregiver to reposition the person. Or if no one was coming along to adjust them, it would actively inflate an air bladder and then move them themselves. So these are great collaborations. Again, I do emphasize that we are all co-inventors and all equal partners in this. That Heather, myself, and two different groups of students. These are both two different senior projects, separated by a couple of years. So we paid for the patents ourselves through the patent lawyer, and now we're actively trying to sell both patents. So we'd like to sell it to a company that could actually go ahead and make these and get them into production and help people. So we're definitely very proud of that. And myself and me and Heather, we have several children together, so we're co-inventors in life too, besides just in engineering. Okay, so basically after spending all that time at Aberdeen Test Center and then Tobyhanna Army Depot, I returned home, and I really do emphasize home, coming back to Wilkes University, because I think I always knew I wanted to be a professor. Even when I was a student, I was a TA, teacher's assistant, and I liked helping my fellow classmates learn the material. So I would get up on the board and I would kind of do example problems for everybody, in my class or the class below me. So I think I always, and then even when I was working at Aberdeen, before I left, I set up a tutelage session of, okay, this is everything I know about outriggers, guys, and this is everything I know about the bridge crossing simulator. And I think even my coworkers were like, wow, you should be a teacher. So I started as an adjunct professor back in 2010, which is 10 years ago. Wow, can't believe it's been that long. While finishing my dissertation. So, as I mentioned, that 2012 is when I got my PhD. So I started just teaching part-time while working at Toby. And it was really after I got my PhD, then I actively pursued trying to get a job full-time here at Wilkes. So I'm going to pause the video and pick it back up.